Our next presentation is from Takaya Nakagawa, who is a sales engineer in NTT Advanced Technology based in Japan. He's been with NTT Advanced Technology Corporation for more than 20 years on both sales and engineering teams. He's responsible for network design, construction, and maintenance in Japan, and in recent years has deployed RPA-based business automation, white box, and optical network solutions outside of Japan. He's going to be presenting return loss problems associated with faster optical networks. Welcome to the Nanog stage, Takaya. Here. There you are.
Hi, I'm Takaya Nakagawa. I'm not used to speaking in front of this much people, so I'm kind of nervous, so forgive me. Okay, so this is the agenda. So I'll talk a little bit about me, myself, and then basic of the optical networks and the down loss and how to deal with it. Okay. So the first one, I'm Takaya Nakagawa. Let me talk about a little bit about myself. My team is developing and manufacturing equipment and tools for optical connectors. We also sell optical connectors in US, so some of you may have seen and used one. The basics. So let me talk about the basics. Now let me give you the briefly introduction of the optical connectors. The optical connectors are components used to connect and disconnect optical fibers. It must be able to connect optical fibers accurately at the low cost to allow the mass use and ease of the use that everybody can use it. Today, I'd like to introduce some of the new problems that has been arisen as the speed of the optical connectors increased and how to deal with them. Let's start by briefly talking about the trends in Internet standard. Ethernet standard. This graph shows the Ethernet standard have been completed up to 800G with 1.6 tera and 3.2 is also in sight. High-speed communications between GPU server is also essential requirement for AI, which we heard a lot these days. As such, higher speed Ethernet standards are being proposed, but optical connectors are always used for the transceiver interface of each standard, making optical connections unavoidable. When these optical connections, new problems are being apparent as the communication speed increase. Today, I will focus on the problem of communication errors caused by the return loss. Recently, we have been receiving more and more inquiries about unknown communication errors from our customers. We often heard that the communication error was occurred after the replacing to higher transmission rate such as 100G from the lower transmission rate. We guess that cause of the error could be the return loss of the optical fiber transmission line, because return loss is specified in IEEE standard with above 25G. Let me explain what return loss is. There are mainly two optical properties are specified at the connection point of the optical fibers: insertion loss and return loss. As you may know, insertion loss is the amount of optical power lost from the sending side to the receiving side. If the insertion loss is large enough, signals is not transmitted to the receiving side, and it causes communication errors or worst case link down, because signal does not reach correctly. On the other hand, the return loss is the amount of the optical power returned to the sender side at the connection point by reflection. It is an unexpected situation and may cause trouble. it is hard to imagine how return loss affects the communication quality. So we have tested. The test environment used 100G transceivers and was configured to create sections with large return loss between connections. By creating multiple connections with the poor return loss, we built an environment in which the return loss could be adjusted to 21 dB or less, which exceeds the limit of specified value. To check whether there were any difference depending on the transceiver manufacturers, we've used the 3 different transceivers from the other companies. This is the test result. You have an interesting result. First, we tested with adding one connection point which has poor return loss under 21 dB, but the bit error did not occur. Then we increased the number of connection points to 3. Then bit error happened. This table shows the result. Bit error were confirmed in all 3 tests conducted by the different transceiver manufacturers. We guess it caused by the multiple reflections. When the poor connection point is only 1, then reflection signal at the connection point goes only to the sender side. But when the poor return loss connection point is more than 2, then reflection signal at the connection point goes to sender side and reflected at the signal again to the other side and goes again and again. And it goes so that the reflection signal goes to the receiver side together with the original signal. This graph on the top is a normal eye pattern without multiple reflections. On the other hand, the lower graph shows an eye pattern in the environment with multiple reflections. When there is multiple reflections, the waveform of the eye pattern becomes distorted and line becomes thicker. This means that waveform of the light transmitting zeros and ones has been distorted. Multiple reflections disrupt the right waveform, resulting in the worsened bit error rate. We've also tested whether the effect of the changing the optical power state when the multiple reflection occurs. The top image shows the eye pattern when the optical power is at -1.4 dB. The next image shows the eye pattern when the optical power is reduced to -6.5 dB. At the same scale, the height of the eye pattern is about 1/3 lower than the image above. The bottom image shows the eye pattern when the optical lower is further reduced to -10.6 dB, almost the lower limit of the optical transceiver. The height of the eye pattern is even lower, and eye opening is no longer visible when compared at the same scale. When enlarging the bottom image, you can see that waveform appears a little hazy. As the result, the eye opening becomes narrower and the overlap at the intersection becomes thicker, which makes it easier for error to occur in 0-1 judgment. If you lower the input optical signal levels significantly, the bit error will start to appear at certain level, and the number of the error will continue increase. In an environment where multiple reflection occurs, the waveform is also disrupted by the reflections. So I think the signal level will be affected even more than the normal conditions. This graph shows received optical power versus BER with multiple reflection point. This is also an interesting result. Even if we received power at our export is enough, such as larger than -5 dB, bit error occurs. This is because the signal degradation by the multiple reflections. This phenomenon is unknown to our customer because received power is enough, but the communication error occurred. This is a comparison of eye pattern of 3 transceivers. Even the same standard product, the shape of the eye pattern is different between the manufacturers. The result of BER tests are different between 3 transceivers. This is an environment where multiple reflections are present. We have confirmed that there are considerable differences in performance between manufacturers in the environment affected by the multiple reflections. Here is a summary of the test result. We confirmed that the multiple reflections caused interference in the transmitting light waves, resulting in degradation. We also confirmed that the optical power level decreased the impact of the multiple reflection of the transmitted light increase. For this reason, optical fiber transmission paths with many optical connector connection points require some cautions. This is for your reference. For the 400G and above, the PAM4 shown on the right slide is the mainstream signal format. The testing we are explained this time was based on NLZ, mainly 100 GB. With PAM4, 4 signal levels must be determined. The amount of the signal that can be sent is double, so that the signal level must be judged more sensitively. Here is another supplementary information. We've tested with the inserting poor return loss connection point into a long distance connection. The distance is 20 kilometers of each. In this case, we did not observe any bit errors, even if there are 3 poor return loss points. So longer distance connection points such as between 2 data centers, it doesn't seem to be much concern. Think the reflection will be gone while sending is a long distance. For the cause of the poor optical properties. From the explanation so far, I hope you understand the multiple reflections cause the communication errors. We are talking about what caused them. Let me explain the connection structure of the optical connectors. The image above shows the connection part of the LC connector seen from the side. The end face of this connector is actually machined to be slightly rounded. The optical fibers are connected to each other with a force that it's just enough to slightly crush each tip. Since this is a physical contact, it is easy to imagine that what would happen if the dirt or some kind exists. As you can imagine, contamination will affect its optical characteristics. We think lots of the problems in the optical networks are caused by the contamination of the end face. We are often asked how much of the impact do they actually have. So I will explain the result of the test to see what happened when there is dirt on the end face. On the left side, there are the reference value for when clean end faces are connected. The middle shows the data when the hand oil were applied. Hand oil were applied to the optical connector end face by touching them with a finger, just slightly touch. As you can see, there is a slight decrease in the optical characteristic. Also, when connector 2 is clean before connection, but dirt will be transferred to another connections. So make sure to clean the both sides before connecting. The next on the right slide shows the data when the dust was applied. Dust was applied by touching the connector with closing. Both the insertion loss and return loss are very poor, And you can see that it has a greater effect on the optical characteristics than hand oil. The next one. I would like to introduce some special cases that are not caused by the contaminations. The first one is that when the connector is partly inserted, if the connector is not inserted all the way, the reflection will be extremely large. As shown in the illustration on the right side, multiple reflection occurs in the air layer between the connectors and end face, which amplifies optical power and generates return light. To prevent this, it is important to always hear and feel the click when inserting connector. And next one. Another special case is a problem with the polishing grade of the optical connector end face. As shown in the table, optical connectors end face are graded, and the grades that you usually use are SPC or UPC nowadays, which result in the clean end face like connector 1. On the left side of the picture. Connector 2 is the right side of the picture is a connector end face made more than 20 years ago. The PC polished grade on the table. This picture is a little small. Sorry, sorry about that. I mistakenly pushed button. So, okay. So the connector 2 on the right side of the picture is a connector end face made more than 20 years ago. The PC polished grade on the table. This picture is a little small, so it's difficult to see, but the surface is a little rough and many scratches. As shown in the table, the PC polished grade has a return loss of 25 dB, so connection point will be poor. It is unlikely that recently purchased optical cable will have this kind of end face conditions, but it is possible when using the cable that has been already installed a long time ago. We previously received a consultation from the customer who has migrated from 10G environment to 100G. When we checked, we found several areas with high reflectivity, but there were any contaminations. The cause was the polishing rate. The problem was solved by repolishing and upgrading to UPC grade. In this case like this, it is important to know that the problem cannot be identified by only measuring the optical power level. As you can see, various problems can occur at the optical connector connection point. The way to prevent or resolve the optical connector's end face problem as explained above, is to first inspect the optical connector's end face before connecting it. Check the end face and clean it if it's necessary. If it is scratched or has an old polishing grade, as explained earlier, you can restore it by polishing it. Polishing may seem difficult, but there are some handy polishing machines available nowadays. Polishing is now easily possible on site, so don't give up if you have an optical connector with an old polishing grade which is harder to replace. Sometimes checking the optical power level of the transmitting path alone is not enough to identify the problems. If you are in an environment where the communication errors occur even though the optical power level is fine, try using the measurement instrument called OTDL. An OTDL is a device that sends an optical pulse into the path and graphs the conditions of the optical transmission pass from the return time and the return of the optical power. As shown in the figure, large peaks occurred at the point of the reflections. It makes it possible to pinpoint the locations where the partially large reflection occurred. So the conclusion. Remember that multiple reflection can be the cause of the communication errors. And also remember that measuring the power level alone might not solve the problems. And always clean the optical connector before use. Thank you very much.
Yeah, Joel Yeagley. I have a question. One of the things that I've recently been exposed to is the presence of CS connectors. And while I realize that the single mode fiber in the center of this thing is only 9 microns wide, are these smaller mechanical connectors presenting sort of physical issues to a greater degree than LC or SC did?
I think so. The interface has you mean the wait. If you have the some kind of microscope to check if it's has a scratch, you can maybe able to use a polisher to fix it. But yeah, the same thing would happen.
Yeah, I mean they're definitely becoming more fiddly. Like we're trying to get 2 connectors on the end of a QSFP or more. Like, I don't know. I mean, I'm sure there are people here who would like 8. But without having an MPO, because then all your connections go down at the same time.
Even with MPO connectors, you can clean or polish it. You can just break by parts by parts.
Yeah, excellent. Thank you.
Hi, Brian Fields. So I'm curious, in your testing here for return loss, did you notice any return loss being better with APC versus UPC when they were dirty? What I'm thinking is maybe the APC is better or something. There's dirt on it.
There's not much difference if it's angled or not.
Okay, but what you were showing here, these were all UPC connectors, right?
Yeah, but you can do the same thing with the APC. You can polish it and you can clean it with the cleaner.
Okay.
So
yeah, thanks.
Thank you.
I have 2 questions. My first question is, when we check the polarity and roll the fiber, initially the RX light levels are not good, but later on the RX light levels come up. So what might be the issue?
It's hard to say. Sorry, I have to look more, I guess.
Is it because of the dust or?
Could be a dust or could be something else. It might be easy if you have some kind of tools to actually look the interface or the transceiver side and see if there's any dust or maybe something else, or it could be scratch.
Okay. And the other question is, on the A side, if you are connecting with 100 gig LR for optics, and if you are connecting on the Z side with 2 by 100 gig LR for optics, is there a possibility of TX and RX light levels look good?
Yes, I think so.
They are compatible, you mean to say?
They
are compatible.
Other part?
I mean to say, on the A side, if we are connecting with 100 gig LR for optics, on the Z side, if we are connecting with 2 by 100 gig LR for optics, is there a possibility of TX and RX light level looks good? That's the question.
Sorry, I couldn't get it. So maybe I'll talk to later. Sure. Okay. Sorry about that. I need some lighting or something. Sure. Sorry about that.
Oh, geez. Lindsay from X Mission. Just wanted to thank you for this talk. It was very helpful because I've experienced these kind of problems with upgrading links. And this does explain a lot of the things that we've encountered. If I just want to summarize, it sounds like you mentioned that these kind of problems don't seem to happen on long distant links with fewer connections.
Yes, the return loss, right?
Yes, the return loss isn't that bad, but it sounds like if it's a shorter link or it has multiple physical connections, and especially if it has lower dB, that's where we tend to see these kind of problems.
Yes.
Okay, thank you. Thank you
Yeah,
again. This is
yeah.
very helpful.
If it's a long distance, it seems like the reflected light will like gone while they are like on the way.
Okay.
So if it's a short distance, it remains, so it goes back and forth and back and forth, and it makes a problem.
Thank you. I think we've been blaming optics or bad optics, but it sounds like we just need to clean these connections and be more aware of this. Thank you.
Thank you.
Joel Yegu again. I actually have a personal anecdote on that, which is that I have fiber paths that are similar lengths in Chicago and Tokyo. The Tokyo fibers are actually about 20 kilometers long, but they actually have to traverse 4 separate fiber providers and at least 8 interconnections for the same path length. And we have much more back reflectance on that. And in fact, there's even 2 flavors of fiber involved. So yeah, when you're assembling a path out of pieces, like that is definitely a property we see a lot. Yeah, more power is not necessarily like not the right answer maybe.
Thank you, Takaya.
Thank you very much.